All right, so we'll go ahead and get started here. Let's see here. I need to make sure the physical science has been posted. Okay, so now that we got that posted, this to me, oddly enough, talking to some of my classmates, that in some cases they're thinking about getting rid of stoichiometry in certain parts of the curriculum. So what does that mean for some of you who have to have this in college? It's our belief if that happens, you're already expected that you would know that going into college, okay? And the problem with this is, like for instance, if you were doing a composition stoichiometry problem, okay? And what that means is if composition stoichiometry would say if you had, we'll say 110 grams of lithium sulfate, we might be asking, well, how much of that is lithium? Well, what happens if you don't write lithium sulfate out correctly to begin with? Yeah, it doesn't matter what you've done the next 7 or 8 minutes. See, I went over that number. I started at 7 or 8. Okay? Is that what you do is probably going to be almost 100% wrong. And that's going to happen in reaction stoichiometry too, where if you don't get the equation written correctly, probably 70 to 80% of the time, what you write after that, it's not going to make any difference because it's going to be wrong. But, so now, should we give partial credit for working on these? You get the wrong answer, but maybe we left out a coefficient. Sometimes that happens, okay? Mistakes are made, and we say 2 things. Try to learn from them and try not to repeat them. All right. So now, tomorrow we're going to start classifying these. Wednesday we're going to start placing what we call oxidations and reductions into these types of reactions, because what's happening on the left side when it goes to the right side? Is it being oxidized? Is it being reduced? Okay. Last year, we kind of made our way through it, but it might not have been pretty, but we made it. Yes, ma'am. What's that?
Can you explain what those mean? Like, I don't remember what those mean, like oxidation and those things. I don't know.
From physical science?
Yeah.
Because we didn't discuss that in physical science.
Well, like what is it, the combustion?
Like the things you drew on the board on Friday, but you told us not to write it down.
Correct. That means how one element is changing from one side to the other. Okay? And the best examples to give are these right here, but I don't want to throw so much information at you at the same time. That's why we got it broke up into different slots like that. Otherwise, in my opinion, it would be overwhelming, like expecting, are you running, getting in shape? Which you should. Why is that? For your chosen, yeah, for wrestling, for your chosen sport. You're not expected to go out and wrestle. I don't know if that's how wrestling practice works, or if it's working on different moves or something to that effect. We wouldn't expect you to do that on the first few days, would we? It's probably more so conditioning more than anything else. It would be too much to expect that from you. Okay. So now, what is it that these 3 reactions, green, I don't know if you want to call that red or pink, I don't know, and blue, what do they have in common? Yes, because those are all what we call combustion reactions. So now, if that is the case, what are our byproducts in these 2 reactions?
So combustion has hydrogen, oxygen, and carbon.
More or less, yes. It could be a synthesis reaction like photosynthesis. That's not combustion. That has carbon, oxygen, hydrogen.
Something else to that.
With these two here,
No, with the synthesis.
how's that different than synthesis?
Combustion, yeah.
Okay, because what's happening, okay, we were just talking about this in physical science, actually. No, that's not right.
But in order for it to be combustion, it has to have carbon, hydrogen, oxygen.
Correct. So when you say, is it always a combustion reaction if it only has carbon, hydrogen, and oxygen in it? Well, this reaction does too, but this is not a combustion reaction. This is a synthesis reaction. Okay?
So why would that one be synthesis?
Why would that one what?
Why would that one be synthesis and not combustion?
Because you're not burning anything, you are making something. You're making sugar. And that's what plants do. You learned that last year in biology. Right?
I don't know.
Oh, you mean that's such a blur?
Yeah.
Okay. So we get the same byproducts in every combustion reaction. This one, and this one. So we can presume with fair certainty that we will get these as byproducts. Okay? The reason I say with fair certainty is because if you were to, I'm going to say look inside of a chimney, but do any of your families, do you burn logs or lumber or wood or anything like that? That smoke has to go somewhere, okay? So as it's going into the chimney, okay, you might not find, you're going to find carbon dioxide, that's correct, but there's a solid form of carbon that you're going to find inside of there. So what happens is the less oxygen that you have, okay, it might be carbon monoxide you might find in there. And with every house, I would presume that you all have carbon monoxide detectors in your house. Okay? Because, and why would we say that that's so important? What about carbon monoxide? Yeah, and would you know it?
No.
Probably not. Okay? So what happens is we've got carbon dioxide, okay? That's true, but if you remove an oxygen, because there's just not a lot of that to burn, that's when sometimes furnaces aren't venting like they should, okay? So now you've got carbon monoxide instead of carbon dioxide, and then as you look in the chimney where there's no oxygen, so it's just solid carbon inside of there. But that's why we say with fair certainty, we are saying that you're going to get carbon dioxide and water as byproducts. And this would be true probably starting now until, I don't know, next April. How many of you park your vehicles outside? Okay. How many of you have your vehicles parked outside? How many of you have had to scrape your windshields lately? Okay, so you could get by without that and just start your vehicle and let it run. How many of you just let your defroster take care of that?
No, I let the window cleaner take care of that. Oh yeah.
Okay.
And then you hit your window wipers. It just takes it right off.
Or it just freezes another coat on top of it.
No, it doesn't. It gets rid of it. I promise.
When it's not that
Well,
cold
for
out.
me,
That's
Really?
really cold
Yeah.
out.
Okay, but that's what I would not suggest.
Did
But
you know that you're not supposed to dump hot water on your windshield because it gets shattered?
I'm out of it.
well, it's tempered glass, so I don't think it would do that.
So I can.
Mhm.
Well,
Okay.
You can also put hot water in a bag and just like
So with those of you who say you just let your defroster, take care of that. What do you notice about your exhaust pipe where all of the fumes come out of there? What do you see about that tailpipe or exhaust pipe?
Anya, tell me.
I,
Maybe like sometimes the black smoke.
The black smoke. She thinks black smoke can come out of her car.
black smoke can come out of your car.
No, she can't roll coal in her car.
I don't know where this conversation's going, but you would want black smoke coming out of there before white smoke.
Yes, but oh my god. Okay, no.
Because does anyone know what happens if you have white smoke coming out of your exhaust? You have coolant going into the block of your engine. That is really bad. Okay? When you see black smoke, that could be from a misfire or anything like that, or backfire. I'd rather have black smoke than white smoke. Okay. So, let me ask you this. So, we'll go like this. So, for those two combustion reactions, box or triangle, which one would you rather balance? Okay. The trap has been set.
Triangle.
You went into it and you sprung the trap. There you have your products, but the equation's not balanced. Okay? So, we had said that you would rather do the box, okay? Now, when you do these, do you remember writing elements underneath your arrow? No. You can do that, or you can just do it in your head. Okay? So with this, when you say we've got 2 carbon atoms here and only 1 over here, what would we do? So let's try putting a 2 there. And that 2 has to be distributed through everything. All right? So 2 carbons, or do you want these wrote underneath the arrow like you did before? You tell me. Okay, we're good? All right. So then the carbons are now balanced. How many oxygens are on your product side?
1. 3, 2. 2.
No, 5. You've got 5. We've got 4 here and 1 on the end. Okay? Now, would you want to work on your oxygens or your hydrogens because we've got 6 of them there and only 2 of them over here? Okay, so let's do this by 3. Okay? So our hydrogens are balanced, our carbons are balanced, but let's look at our oxygens.
Okay, so now you have 7 oxygen, right?
We do.
You need an even number.
And this does happen, but this is way too advanced for us.
Yeah, that's
Okay.
what it would be.
That's what it would be, but we don't do half reactions. Okay? I mean, there are applications in chemistry where you would do that, but this is not one of them. So now, when this happens, well, now we got to start over because that just didn't work out. Okay? Our explanation that we gave is, let's say, for instance, you could be a quarterback or you're a point guard. Okay? I don't know which you want to pick, quarterback or a point guard. Okay? So then what the point guard's responsibility may be is as you're bringing the ball up the court, chances are the coach is going to tell you this beforehand, is if you have a person guarding each and every individual as opposed to your opponents are just standing in the lane. on defense. What's the difference?
That's called a zone.
That's called a zone defense as opposed to man defense. Okay? So it's your responsibility to know the difference. How we take an approach to this is in these combustion reactions, we look at our hydrocarbons. Okay? If this is even, if you remember from 2 years ago, once you recognize that, just like you recognize what defense you have, I know I need to do this right away. Okay? Let's see once what happens. What's 2 times 2?
4.
Okay? So we got 4 carbons and only 1 over here. So let's try putting a 4 there. Okay? So that is 9 to 2 with our oxygens. So then maybe we should look at our hydrogens then instead.
So if you start with the carbon, you times by 2.
Not always,
If it's an even number.
if it's an even number. But even then, that's not the case. Is it an alkane or an alkene? That's also important.
Wait, so.
Okay? So now, what is 2 times 6? I would recommend always doing your oxygens last. Save them for last. Okay? 2 times 6 gives you 12. We've only got 2 over here. We take that times 6. Okay? Our carbons are balanced. Our hydrogens are now balanced. Now let's go ahead and look at our oxygens. 2 times 2. Or no, excuse me, 4 times 2. And then 6 times 1. So 6 plus 8 gives you 14 oxygens.
So then you need 7 over.
We need 7 of them. Your equation is now balanced. Okay? So then we said, remember this had a box, this one had a triangle. Everyone picked the box. Now, I would expect that because the reason you picked it is because that number was smaller.
Yep.
Okay? So let's go ahead and look at this one now.
2, 7.
So now that this is an odd number, okay, but we know that this is an alkane, this is an alkene. These are 2 totally different organic families. That's going to be important in just a moment because if we've got 5 carbons here and we've only got 1 over here, now we can jump right in and say we're going to take that times 5. Okay? Our carbons are now balanced. We're going to save our oxygens for later. We've got 12 hydrogens. How do we get 12 over here? Okay? If we take that times 6, now notice 5 times 2, 6 times 1, so that gives you 16. So now how many oxygens do we need? Or we need to get that up to a 16. So we take it times 8. So that's the difference between these types of hydrocarbons and these type. Here you have an odd number, here you have an even number. That only works with alkanes. Alkenes is just a little more difficult to do. So now, let me ask you this. Purple, blue, or maroon and bronze or whatever. The blue one. Okay. The reason these are written next to one another is we apply this same logic. We say, oh, well, if this is an odd number, I can just jump right into it on this side. Well, let's take a look. 3, what would we logically put here? Okay. We've got 6 over here. Okay, how are we going to get 6 hydrogens over here? Okay, so now everything's balanced except for our oxygens.
Except that wouldn't work.
That doesn't work. But it's an odd number though. Isn't that supposed to work? We just said if it's odd, go ahead and balance that into there. But remember, This is an alkane. This is an alkene. Those are two totally different organic families. So now, since this is odd and we can see that this doesn't work, well, I guess the best thing to do is probably start over. And I would agree, that probably is the best thing to do. Okay, now we're going to say, since that didn't work, let's take this times 2. Okay, that gives you 6. We only have 1, so we need, okay, save the oxygens for later. Let's look at our hydrogens. That gives you 12. And how many of them? We got 2 over here. How do we get this up to a 12? Okay. So everything's balanced except for our oxygens. So 6 times 2. 6 times 1. Okay, so 6 plus 12 gives you what? And divide by 2 would give you 9. Okay? So that's why it's important to be able to recognize this.
So is the first one an alkene, like the one above?
This one is an alkane as well. Okay? The reason we know that, when you have twice as many hydrogens as you do carbons, you know that's an alkene. But if you have twice as many plus 2 more, now you know that's an alkane.
So what is it? Twice as many? 12?
Yeah, if you have twice as many hydrogens as you do carbons, you know that's an alkene. If you have twice as many plus 2 more, now you know you've got an alkane. And this is why. You could write this structural formula out like you did when you were a freshman. There's our 2 carbons, okay? 1, 2, 3, 4, 5, 6. There's where your 6 hydrogens are. Now, the reason we say that, we've got twice as many. So 2 times 2 would give you what? 4, right? 2 times 2. Twice as many would give you, twice as many as 2 would give you 4, but you have to count the ends here. So then with an alkene, do we remember the difference between that besides naming with organic compounds from 2 years ago? Okay, what that means is there's a double bond in there. So now there's our 3 carbons, so there must be only 6 hydrogens. 1, 2, 3, 4, 5, and 6. So there's our alkene. Alkene's got double bonds, alkane's got single bonds. All right. So, front row, are we on the bus here? Back row, are we on the bus here? All right. So we can get rid of this. Get rid of this. All right. Sometimes when I'm guessing, and I think it's a pretty good guess, is when you take your ACT test in the spring, they might give you a periodic table and they're going to say you have to write some of these compounds out. I don't know how accurate that is, but I would presume it is. Okay? So what is the symbol for lithium? What is the sulfate ion? That's lithium sulfide so far.
And lithium's a +1 charge.
That would be if it was lithium sulfide. If you can't find this, it must be on the backside like you had just correctly flipped. Nope. SO4. Always start with your negative charges. SO4 has a charge of negative what? Lithium has a charge of, okay, what's your least common multiple?
2.
So we need a 2 here. 2 times 1 gives you positive 2. Negative 2 times 1 gives you negative 2. All right. What is sodium? And the chloride ion? Okay. Then, what's lithium chloride then? Do we need to change anything? No, because they balances out to 0. And then what is sodium sulfate? We know sodium is Na. You're right. But do we want to go back and see why that's right? Because we can just go ahead and write out the formula right away and be fine. But let's figure out. You're right. We're not going to take anything away from that. What is the sulfate ion? Okay, and remember, this has negative 2. This one has plus 1. Least common multiple is 2. So we need a 2 there. All right. Does this look difficult to balance? And it's not. The reason it looks maybe difficult is because you have these polyatomic ions in here. And if you remember from freshman year, we would say keep your polyatomic ions together. That's just a good way to look at this. Don't split up your sulfur and oxygen. You can, but it's just easier to keep them together. All right. So we have 2 lithiums on this side and only 1 over here. Okay. Then what does that do to your chlorides? Okay, so we have 2 chlorides there and only 1 over here. And that is right. Everything balances out now. All right. These bottom 2 is probably the more difficult ones. Okay? One of them has no reaction to the purple reaction. Our front row, are we good with that? And back row. Okay? Because when you look at this, okay, there's a reason why we have this on the back of your periodic table. And it is on your right-hand side. It's called your activity series. When something is more active, that's the only way it can replace something in a single replacement reaction. That's where this activity series is useful, only for our purposes, only in this type of a reaction. Okay? What I want you to do is locate who is more active, copper or zinc. And I don't expect you to know that. That's why you have this on your periodic table. Zinc is more active. So think about that is if it's more active, you could say it's got more strength than copper because it's higher in the activity series. So if it's higher in the activity series, that must mean that this zinc can boot that copper out of there and replace it. Only once because it's single replacement. The other way can't happen because copper is lower than zinc in your in your activity series. So if that's the case, this we'd say is less active. This is more active. And I just threw that up there since this is more active than this. This can't replace that. So you take copper, you pour it into a zinc sulfate solution, and nothing is going to happen. You're just mixing 2 things together. The copper, you're just going to ploop down to the bottom of your solution and just hang out there and do nothing. On the other hand, this zinc plus copper sulfate, that does react. But we can pick up with that tomorrow because I think we've done a lot today and it might be a lot to process. I want to give you time to decompress take a deep breath, and we'll continue with this. Not only just the balancing, but the classifying tomorrow as well. We'll catch up to you next time.